So for the best case, we just look at the most balanced partitioning. Okay? Two subarrays, S region, L region, they have the equal size. All right. So look at this. The best we can get. Okay? Each one approximately 1/2 of the original problem size. Okay? For the elements in the S region, we don't need any swap to put them there. Yeah. But for elements, if we want to place them in the S region, we may need to do several swaps. Okay? Yeah. But how many? So it is very hard to estimate. All right. So we can easily derive this recurrence relation. Here you can see for the base cases, when you have one element, no comparison needed. When you have two elements, you only need one comparison. Okay? Then you split the problem size approximately, so here approximately 1/2 of the original problem size. And in order to do the partition, you need to pay this cost, big theta of n. Right? Or in other words, we need to use some constant function c times n here. C times n. Yeah. So here the expression we use here, big theta of n, in this recurrence relation, it is not a very rigorous math way. We understand the meaning of this equation, but we have to say this is not a rigorous way to write the formula. Okay. All right, so here let's assume some term like this. Replace big theta of n in this way, then it is a rigorous math expression. Okay? All right. Next, we will use this recursion tree method. Remember, we used that before. So we used that several times before. It is very effective. I hope you can do that by yourself. Yeah. Here it's a simple example. Yeah. All right. Recursion tree with constant. Okay. All right. First, we assume our n and the k in this relationship. Okay? Yeah. Because in this way, we try to figure out how many levels we can go in this recursion tree. We try to estimate that. First, at the root, we put a non-recursion cost, Cn. Then we split, we put the non-recursion cost, because the recursion terms we can split further level by level, so we do the split like that. Okay, all the way down to the bottom, so that's the bottom level. Yeah, so that's why, because we use that estimate to determine the bottom level. Okay. Yeah, because the size, problem size is less than or equal to 1, the problem size. So we can say all these bottom level terms are zeros. Okay? So we only need to collect all the non-recursion cost in all the levels. Yeah. Each level we know it's n. So Cn, this level also Cn. This level also Cn, or any level it is Cn. How many levels do we have? K plus 1. And the K is in approximately log base 2 of n. So then the cost estimate big theta of n log n. Okay? So that's the best case. Pretty easy. Yeah. But the average case is extremely hard because we cannot control how to split any given array. We have no idea where is the partition element, pivot. We have no idea, so it's very hard to estimate. Yeah. So that's why we cannot do any analysis here for the average case efficiency. Yeah. All right. Next, we have several issues. Yeah, so we finished that analysis of the efficiency, but we still have a few more small questions to discuss. The first one, how to improve the performance. We know the poor performance is due to the unbalanced partition. If we can make the partition more balanced, we can avoid the bad worst case. So the idea is like this. Randomization technique. We try to use randomization to avoid the worst case. Unbalanced partition. Okay? Yeah. Use the last element as the pivot may have bias. Okay? So we want to eliminate that possibility. Okay? Yeah. How do we do it? Random sampling. We do random sampling. Okay? Array elements, we select any element randomly, anywhere. Yep. So we try to break any bias pattern. Yep. Select a random element from the array. Then, because we want to put it at the end of the array, so we do one swap. We can make it the last element, but we need to use one swap. Okay, yeah. Then we do partition on that. Okay, so this is the simple randomization technique. Very simple. Yeah. Can we improve? How much we can improve? We don't know. Okay, yeah. All right. Another technique called the median of three partition. So from this name, you can guess how do we improve partition against unbalanced divide, right? Yeah. Go avoid the extreme cases for the pivot. Yeah. Randomly select this time 3 elements, not 1. Randomly select 3 elements. So try to, avoid the bias even more. Yeah. And for these 3 elements, we can find the median of the 3 using 3 comparisons. You need to do more work. Okay? Yeah. Then use that median as the pivot. Use that median as the pivot this time. So we can, in this way, because the cost is higher, so we hope we can make the partition more balanced. Okay. All right. The result, the overhead is a little high, so we pay a little overhead. The occurrence of extremely unbalanced partition is greatly reduced. Yeah. How much better? It is very hard to give you the answer. How much better it is improved? It depends. Yeah. So very hard to answer this question. Yeah. All right. Examine the swap operations. We have swap operations. Yeah. But how many? It depends on the input, right? A swap operation is more expensive than a comparison. We know that. We need to make copy, right? So we need to make copy, like that. So that's slower than one comparison. Okay. when do you get the maximum number of swaps? So can we get that? The maximum in each partition, the maximum number of swaps? It looks like that the question not that easy to answer. Yeah. Although here I give you a simple example, yeah, but for the general array, how do you know that? Right? Number of swaps. Okay? Or you can estimate, yeah, because it's not it is not an easy question. So, but it could be a research problem. So people can study that. Interesting question. Yeah. All right. The last thing I want to talk about, in-place sorts. We have this concept before, in-place sorts. So here, let's look at another time. The meaning, other than the original array, only use a constant number of extra locations to store data. Okay? That's the meaning, the definition. Constant number of extra locations other than the original array. Okay? So let's look at all the sorting algorithms we have learned at this point. Selection sort, bubble sort, we know selection sort in place. Yeah. So, try to extra space. Look at extra space we need to use. Yeah. Very little. Yeah. Bubble sort also in place. Yeah. Insertion in place. Okay. Yeah. Merge sort not in place. So we need a lot of extra space. So remember when we merge, also recursion. Remember the merge sort, we need to do recursion. Yeah. Even the merge step, auxiliary array, right? So we need to copy, Yeah. So the merge step, not in place. But the quick sort, so here the question for the quick sort, is it in place or not? This question, so we need to answer for different cases. Yeah. First, the partition step. The partition step in place. So we saw that, right? Yeah. 3 extra spaces, 3, yeah, constant number of extra locations. But that's only for the partition step, each partition step. Okay. Remember, we have recursion, we have stack, Then we need to use extra space, right? Recursion, extra space. Yeah. So for that, we cannot say in a clean way, in place. Yeah. In my opinion, I may like to say that level 1 in place. Call it level 1 in place. The partition step. Okay, so the step, but it's not level 2 in place. Recursion. There is another level. Okay, another level, level 2. So not level 2 in place. Because at the recursion level, it is not in place. Okay? Yeah. So we should be very careful about this quick sort. Okay? All right. So that's what I like to talk about for this topic. So we finish this lecture, Lecture 7, Part B.